In this video, I will discuss matrix notation in the context of regression analysis. It is very common in econometrics to express a regression equation in matrix form. So I illustrate how this notation works, and in additional videos you will see that there is a benefit of using matrix notation. On the whiteboard, we have a regression model where yi is our dependent variable, which is explained by two independent variables, xi and zi. And then we have the error term epsilon I that follows the usual assumptions. And you see a constant term alpha and slope coefficients beta and gamma. The beta and the gamma, they capture the partial impact of the respective independent variable. In this case, we could assume that our dimension is a cross-section, but it doesn't have to be. It could be also a time series. So running from 1, 2 up to, say, capital N. So we have a standard cross-sectional data structure. Now that basically means that our equation 1 can be written n times for each and every cross-sectional unit. Now it might be fun to do this, but of course there is a much more efficient way of writing this regression using matrix notation. The first step is to use column vectors to express this system of equations in a single line. We could simply write y1 for the first cross-sectional unit, y2, and all the way up to yn is equal to a constant term. Now this constant term needs a 1 vector because it is in all these equations. So it has to match in terms of dimensions. We need in this case capital N1 as our dimension. Yeah, so we have n rows, 1 column, n rows, 1 column. And of course our alpha is a constant term, so that's a so-called scalar, has dimension 1, 1. And then we have beta. And here we have our first independent variable. And again, we can write this all up to xn. So I added the second independent variable as a column vector and then the column vector of the error term. So we are done. We have now a nice expression in one single line for these n equations. And now we can introduce some notation to simplify our work. This column vector is simply written as y, and if you see this in a textbook, it's usually expressed in bold font. We can't really do bold properly on a whiteboard, so we just underline to indicate that this is actually a column vector with dimension n times 1. The dimension is obvious from the context. And then we have our scalar alpha, and then we have the all 1 vector. So again, I indicate it's a vector using the underline, plus beta, the x vector, plus gamma, the z vector, plus epsilon, our error term. Now this is already a nice way of writing it, but not yet very common. The next thing you see is that we combine these column vectors on the right-hand side into a single so-called data matrix. Now the data matrix contains our data which we use to understand our dependent variable y. And it's convenient to combine these vectors because then we can use matrix calculations to derive, for instance, an OLS estimator. So what we do is we combine them. First we note that because these coefficients are all scalar, so we could easily move them basically to the back without any issue whatsoever. And we could rewrite this as follows. So it will be y And when I put this into a matrix here, we have the all1 vector. And then we have the x1, x2 vector. And we have our z vector. And then we have the alpha, the beta, and the gamma, again as a vector, and I will talk about this in a minute. Now here we have to understand a bit about matrix multiplication, and I will do another video to explain this in a bit more detail. To multiply a matrix, we take the first row times the first column. So in our case it would be 1 times alpha plus x1 times beta plus z1 times gamma. So it would just give me the equation you see above. It's always helpful to think here about dimensions. We have in this case n rows, and on the left hand side it's an n times 1 vector. Our error term is also n times 1. And you see we have 3 columns. So 1 column for each of the independent variables plus the constant term. And this is here our often called parameter vector. It's very common to use theta for this. And you see we have 3 rows and 1 column. And now in matrix multiplication, these adjacent dimensions have to match, which they do. And the outer dimensions are the dimensions you obtain after doing the multiplication. And of course they have to match in this case, so it has to be n times 1. It's always nice to check dimensions. So we end up then with y vector equal to the data matrix X. It is common to use a capital letter for it. And then we have theta, which is our vector that captures our parameters plus epsilon. Yeah, and we are done. So here we have it. That's in a very compact way our regression equation expressed in matrix form. I see you in the next one.